Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Physics. We will keep to our tradition and start in Swedish and then continue the presentation in English. And you are of course welcome to ask questions later on in either language. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. På min ena sida sitter professor Olle Eriksson, ordförande för Nobelkommittén i fysik. Och på andra sidan professor Göran Johansson, ledamot av Nobelkommittén för fysik och sakkunnig inom ämnet. My name is Hans Ellegren. I'm Secretary General of the Royal Swedish Academy of Sciences. To my right is Professor Olle Eriksson, Chair of the Nobel Committee for Physics. And to my left, Professor Göran Johansson, member of the Nobel Committee for Physics and one of the experts in this field. Årets pris handlar om att möta kvantmekaniken på en ny skala. This year's prize is about encountering quantum mechanics on a new scale. Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i fysik till John Clark, University of California at Berkeley, USA, Michel Devoret, Yale University och University of California at Santa Barbara, USA, och John Martinis, University of California, Santa Barbara, USA, för upptäckten av makroskopisk kvantmekanisk tunnling och energikvantisering i en elektrisk krets. Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Physics to John Clark, University of California at prize.
Yes, thank you. So, this year's prize is about quantum mechanical tunneling. This is a quantum mechanical effect that was discovered soon after Erwin Schrödinger published his famous wave equation in 1926, almost exactly 100 years ago. Soon after it was published, solutions were discovered where a particle could penetrate a classically impenetrable barrier. So to the left here, you see that exemplified by a wall, and the little boy throwing a classical ball onto the wall. It always bounces back. However, quantum mechanical particles can sometimes appear on the other side of this classically impenetrable wall, and it is as if it digs a small tunnel through the barrier. Hence the name. Soon after tunneling was discovered, it was also discovered that it's not only an astonishing theoretical prediction, it also has practical implications in the subatomic world. So to the left, you see a big nuclei, lots of protons and neutrons, and so-called alpha decay of this nuclei can be explained by the fact that the alpha particle, 2 neutrons and 2 protons, is bound, it's part and bound to the nucleus by a barrier. And classically, it would never ever leave the nucleus. However, due to quantum mechanical tunneling, it can appear outside of the nucleus, and thus you have radioactive decay. And the fact that it's quantum mechanical tells that it's a completely random process. And also by calculating the width and the height of the barrier, you can calculate the average waiting time for this decay or the half-life. So, we understand that quantum mechanical tunneling is important in the subatomic world. However, can we observe larger systems that time? This was a question raised by Nobel laureate Anthony Leggett in 1978. He suggested that it should be possible to observe something called macroscopic quantum tunneling in a superconducting circuit. So how should we understand this? Well, in the upper picture here, you see a normal conductor. In the normal conductor, the electrons are very individual. They are fermions, and they are very easily distracted. So if you push a current through this conductor, the electrons are easily distracted, and there is resistance. Thus, you always get the voltage across this conductor. In the second picture, you see how a superconductor works. Here, the electrons take each other 2 and 2 by the hand, and then it's much harder to distract them. So then they can lead a current without any resistance at all, so there is current without any voltage, a supercurrent. In the lower picture you see another example, you see also an illustration of how this works. It's actually so that all of the Cooper pairs lose their individuality altogether, and they all condense into one macroscopic state. So it's one Cooper pair condensate, which is determined by one macroscopic wave function or a superconducting order parameter. And you see there is a small gap between the 2 conductors in the lower picture, and that's the so-called Josephson junction. So in 1962, Brian Josephson predicted that you could, even if there is a small weak link or a gap in the conductor, you can still have a supercurrent. And he derived simple equations for how the current and the voltage in this junction relates to the macroscopic wave function on the 2 sides of the weak link. And from his description, you can do the following. If you push a current through the Josephson junction, it can then appear in 2 different states. One without the voltage, and one with a measurable voltage. And the switching between the 0 voltage state and the state with the voltage is, there is a barrier in between. And by detecting how this switching occurs between the 0 voltage state to the voltage state, this is how our 3 laureates managed to prove that there is macroscopic quantum tunneling. So, to the left you see an illustration of macroscopic quantum tunneling. So, our 3 laureates positioned, they pushed a current through the junction, and it was in a state so that it should not classically be able to switch. And yet, it switches from the zero voltage state to the state with the voltage. Although classically you see that it cannot switch. And if you're a physicist, you might realize that the smoking gun evidence for this macroscopic quantum tunneling are when the black dots here deviate from the diagonal line. That's where macroscopic quantum tunneling dominates. So the three laureates, so this breakthrough experiment was performed in 1985 at Berkeley, and the group leader, John Clark, had long experience of working with Josephson junctions. John Martinez was a senior PhD student at the time, and Michel Devoret was a postdoc coming from Saclay outside of Paris, with experience from low-temperature physics, but not with Josephson junctions, molecular solids. So, this trio did not only do this breakthrough experiment, they also did another breakthrough experiment the same year. So, the name quantum physics comes from the fact that atoms absorb and emit energy in packages, so-called quanta. And by irradiating the Josephson junction with microwaves, they could verify that this macroscopic object absorbs energy in a quantized way. So there are quantized energy levels. So, yes, I just want to mention also that in this system of the Josephson junction, there are billions of Cooper pairs. So it's really a macroscopic object in that sense. Okay, so this might sound a little bit abstract. However, this is a sketch of this experimental setup coming from John Martinez's PhD thesis. So you see the scale bar to the right, 1 centimeter, and there you see the silicon chip with superconducting wires, and the Josephson junction is exactly where the two wires meet. You apply the current to the left at the power connector, and then you measure the voltage at the same place. And when you radiate with microwaves, you do that in the microwave contact on top. Then you also see there's a copper tubing and copper powder inside, and that's a newly developed filter for this experiment that isolates the Josephson junction extremely well from the environment, which you need because these quantum effects are very sensitive to interaction with the environment. And I think to make it even a little bit less abstract, I also want to show you a modern quantum chip. So the silicon chip is the square in the middle here. There are superconductors on top. And then there are 9 artificial atoms on this chip. And you can see them with your naked eye. So, the 3 laureates has established, so the picture illustrates how they have taken quantum tunneling and quantum physics from the subatomic world onto electric chip. So now we have 40 years of lots of groups in the world exploring quantum physics on a chip, engineering artificial atoms, exploring quantum physics in regimes which are hard to get to with natural atoms, because you can engineer these artificial atoms. You can also couple the superconducting atoms to mechanical oscillators, and then you probe quantum properties of mechanical oscillators. And you may also have heard that this is one of the platforms where you can develop a quantum computer. Thank you.
Thank you, Göran.
Yes, you do.
Good morning, Professor Clark, and congratulations to the Nobel Prize in Physics.
Thank you so much.
Was this a surprise for you?
So, to put it mildly, it was a surprise of my life. And I'm very sorry my two colleagues are not with us.
I'm sitting here in this beautiful session hall of the Royal Swedish Academy of Sciences at the press conference with many interested journalists here from the national and the international press. Are you ready to take some questions from them?
Yes.
ST?
I have to congratulate you on the award, of course. My first thought was that it's quite mind-boggling, your discoveries. I was wondering, did it occur to you at the time that that you managed to prove there is microscopic quantum tunneling, that it might be the grounds for a Nobel Prize in Physics?
I think that had not occurred to us in any way.
Pardon, I didn't get that.
I think that it had not, we have not realized in any way that this might be the basis of a Nobel Prize.
Do you remember the specific breakthrough and what happened at the time?
Well, Bishop Debray and John Martinez are brilliant people. I worked very closely with them for at least a year on this and other topics. And the first thing I would like to say is that this discovery would never have happened without the two of them. The others in principle would need to have the group, of course, but their contributions are just overwhelming.
Okay, one question there, please.
Hi, Professor Clark. This is Yiwei from the Chinese Media International. First, congratulations, and I would like to know your feelings now and where you are now. And the second question is, what do you think your research has left the open questions for the next generation of physicists? Thank you.
Well, first of all, my feelings are that I'm completely stunned, of course. It had never occurred to me in any way that this might be the basis of a Nobel Prize. And I'm sorry, what was your second question?
My second question is, what open questions does your discovery leave for the next generation of physicists?
Well, I think that, as already been suggested, this is something that does keep to the further development sorry, I'm losing my words, as a quantum computer. I mean, many people are working on quantum computing, and I think that as we see that it's recognized that our discovery is in many ways the basis of this.
Yes, please.
Thank you. Bogu Ravetsky from the Polish television. Congratulations, Professor. I wanted to ask you because, everyone in this room has a smartphone and we have cameras that use nanochips that are actually based on the effects that you were studying. I want to ask you, did you predict when you made your discoveries that they are going to have such a widespread practical applications? And what do you think is going to be the next step in that regard?
It certainly